This conference will now be recorded.
Very good evening, students. Today we'll be learning a very important and very interesting topic called cyclotron. So the cyclotron is used for accelerating charged particles. Okay. So cyclotron is used for accelerating charged particle. We'll see its working principle, its construction, its uses, and corresponding uh, numerical expressions, and if possible we will take up few numerical problems as well. So let us start with our discussion. So it's cyclotron. So it is a device which is used to accelerate charged particles like proton, deuterium, alpha particle, etc. So what is the working principle? So what is the working principle of this cyclotron? The principle is that we have learned already crossed electric and magnetic field. If you remember, suppose this is B, this is E, crossed electric field and magnetic field. So if electric and magnetic field, they are in two perpendicular directions, then they are called crossed electric and magnetic field. So here we will see crossed electric and magnetic field we'll be using here. Okay, in this. So this was actually invented by EO, Lorentz, and MS Livingstone. And Livingstone, MS Livingstone. Okay, so cyclotron was invented by these two scientists. And these were actually invented by Berkeley, like in Berkeley University, California in 1934. Berkeley University. Okay, sorry, California University, Berkeley. What is the principle? See, a charged particle can be accelerated to a very, very high energies, okay, of the order of millions of electron volts. They are made to move in a circular path by applying crossed electric and magnetic field. So this is actually a working principle that charged particle like alpha particle, alpha particle, proton, deuterium, etc. will be accelerated to very, very high energy by making it uh, making the charged particle move in a circular path repeatedly by applying cross electric and magnetic field. The frequency of revolution does not depend on the speed of the particle, neither it depends on the radius of the circular path. So this is very, very important. So energy gained by electrons by repeated circular motion does not depend on the frequency, neither it depends on the radius of the circular path. So this is somewhat the working principle. Okay, so we'll see what is the construction of cyclotron? What are the parts it does have? So what are the parts it has? We'll see. It consists of two cylindrical, hollow cylindrical disc. Okay, hollow cylindrical kind of. These are kind of disc or hollow cylindrical disc, and these, I'm sorry, these are not the thing. I am just talking about this one. So these are hollow cylindrical uh, kind of this actually. Okay, so it looks like English letter, English alphabet D, but it is kind of this. Okay, so this is hollow. You can see kind of cylindrical, part of cylindrical. Okay, hollow cylindrical, and these are metallic actually. Metallic D's. These are called D's. You will see these are D's. D's means D's. Okay. Oh, sorry. D1, and if I write plural, so D's. So these are two metallic, see, hollow metallic D's actually. Okay, these are metallic D's, and as I said, they are actually kind of this. They look like D, English alphabet D, but these are kind of this. Okay, D's. And how, why the name of this metallic semicircular disc are called disc? Because they are of D shape. Okay, English alphabet D. You can see this. This is one D, and another D is this one. Look, this one. So this is one D, another is this one. Okay, so these are Ds, metallic Ds, and these are actually hollow. Actually, you might see here this as actually a kind of disc, but these are not disc. Actually, kind of not semicircular. You can think of a hemisphere, maybe hemisphere part like this. Okay, one is this way, another one just opposite to each other. So these are two metallic discs like this. Okay, and there is a gap in between metallic discs. There is a gap in between. Okay, so these are Ds. So the central part of this here, you can see that. So most of the time, the charge particle actually moves inside the Ds. So charge particle will move inside the Ds. Okay. So these are named as D1 and D2. They are named as D1 and D2. Now, these are actually mounted inside evacuated chamber. Evacuated chamber means there will be no air. Okay. So this whole thing actually, this whole thing, uh, this whole thing will happen inside an evacuated chamber, and you can see very powerful magnets, electromagnets, very powerful electromagnets. This is north pole, this is south pole. So very powerful magnet actually is magnets are kept vertically. You can see the magnetic field lines will come like this. Okay, north pole to south pole. So this is vertical magnetic field. That means if the charge, if this is in a plane, magnetic fields are like this. So you can see the magnetic field lines are perpendicular to the D's. You can see that. Again, these D's are connected. See, these D's are having a gap in between. At the same time, these D's are connected to a very high frequency alternating current source. This one. See, these two are. So this will give you the electric field. Okay, alternating electric field, which will be changing electric field, or alternating electric field, and that is in plane. Okay, this is in plane. Electric field lines will be at some time like this, and that exists only in this gap region. This electric field exists only in the gap region, and that is parallel to the plane, or they are in plane. They are in plane. So you can see this is electric field direction and this is magnetic field direction. So what you see that we are using cross electric and magnetic field. Okay. So these are connected to a very high frequency alternating electric field of few hundreds of kilovolt. So this is actually, this source gives a field of some hundreds of kilovolt. Okay, hundreds of kilovolts. All right, so this is up to here. Now what we will have, there is a small gap between D1 and D2, I have already told, and the charge particle is kept, see, in the gap region. See, the source of the charge particle is kept somewhere in between and inside, like in the region, gap region. As soon as the charge particles are emitted from the source, suppose alpha particle, then it actually first reaches to, suppose this is D1, this reaches to D1. When it reaches to D1, and the charge particle will be subjected to magnetic field only when they are inside the Ds. Okay, otherwise they will not be affected by magnetic field. That means magnetic force will not act on that. Since magnetic field is like this, and the charge particle is entering like this with the velocity, so from the gap region to the Ds, so what will happen, you know, so this is 90 degrees, so the charge particle will be moving inside the Ds in a circular path. And since these are of semicircular shape, before it completes its complete revolution, see, there is a gap in between. So the charge particle, suppose it enters into the D1, then it will be subjected to magnetic field, and there will be circular motion. It will actually move in a circular path, and suppose it enters, see, enters to the D here and come at this region. When the charge particle, after completing the D, it is just coming near the gap region, the alternating voltage will be, like, its polarity will be such that the charge particle will be just pushed to the other D. But during this pushing, it is actually gaining kinetic energy or gaining energy. So it will just move with increasing speed. It will move with increasing speed to the other D. Okay, and also since the energy increases, speed increases, so the velocity, see, the radius of the circular path also will change in the other D. Okay, so it has radius up to here like this, and then when it jumped into the other, see, it is moving in a greater radius. Okay, around a greater radius like this. So when it again come to this region, okay, the electric field is synchronized in such a way that the polarity of the field will be such that the charge particle will be pushed to the D1 again. This is how charge particle will be gaining in gaining energy while moving from one d to another d, because that time it will be subjected by electric field, and it will give certain acceleration that would increase its speed, and then radius also will increase. So that's how the charged particle will start motion like this, and it will continue to move until it leaves the disc. So this is a kind of spiral. So it is a spiral. So the trajectory of the particle will be kind of a spiral. Okay, kind of a spiral. All right. So what happens? This is how the charged particle will move from one d to another d, one d to another d with increasing speed, increasing radius, and thus it actually acquires kinetic energy higher and higher. See, you cannot imagine that it can gain energy up to actually it will gain very large energy. Okay, so I hope you have understood this principle. So electromagnet, I have told these are electromagnet, so to produce a very high electric magnetic field. And see, this is alternating voltage which is connected, like alternating source which is connected to the disk, which will give horizontal or in plane electric field, and this will give magnetic poles, or electromagnet will give vertical magnetic field. So there is cross electric and magnetic field, kind of that. Okay, so now we have understood how, see, when the charged particle gains a sufficient amount of energy, then what happens? Uh, there is something called deflectors. Okay, deflectors, that is also actually a magnetic field only, deflector. So when this see, when the charged particle moving inside the disk, and it acquires sufficient energy for our purpose, then what happens? There is a deflector. So that deflector, that is also actually made of magnet. So that magnetic deflector will deflect the charged particle to come out of the D through a channel. Okay, and then that energized electron will be collimated to the respective, that they will be actually collimated to the target. Okay, so this is cyclotron, and you know the cyclotron, as you know, there is a kind of circular motion is happening here. So we can actually we can find out few parameters of cyclotron, like cyclotron frequency, time period of revolution, maximum kinetic energy gained by the particle after completing its acceleration or motion inside the disk. So those parameters we can actually find out. See here, since the magnetic field is like this and charged particle enters like this, so there is 90-degree angle. So I can write QVB if the charged particle has charge Q, mass m, and velocity v, and v is the magnetic field induction. So QVB is equal to mv square by r. R is the radius, suppose the radius of a particular spiral. So from here we can actually find out. So v1 v can get cancelled. So we can find out the radius of mv by qb. This we can find out, or if we want, what is the time period and all. So we can find out. See, time period will be cyclotron parameter. Let us say parameter, cyclotron parameter. So we'll now find out few cyclotron parameters like radius of the spiral. See, we found out that this will be q v by mv by qb. Now what is period of uh, revolution? Period of time period of revolution, that will be found out from 2 pi r by v. V let it be, we will just put the value of r. R is mv by qv. So we can see this is v. So 2 pi m by q into b. Okay, 2 pi m by qb. This is time period of revolution. Okay. Now what is the maximum kinetic energy of the accelerated ion? Okay, maximum kinetic energy of the accelerated ion. Ion means ion or charged particle, anything. So half mv square, right? We know mv square by r. Let us say for a particular orbit, v0 is the velocity in that orbit, r0 is the radius of that orbit, and this is qv0b. So from here we'll get, anyway, we'll get v0. So v0 is qb by v0. From here we'll get v0 is equal to qbr by m. So now if we calculate maximum kinetic energy, ke max, maximum kinetic energy, that will be half m v0 square, half m v0 square. V0 square means b square q square r square by m square. I hope this is the thing. Yes, q square b square r square by m square. So this will give you, this m will cancel one m here. So b square, this is r0, b square q square r0 square by m, 2m. So this will be actually the maximum kinetic energy attained by a charged particle when it is accelerated in a cyclotron of radius. This r0 is actually the radius of the d. Okay, r0 is the maximum radius of the d. See, radius of d, radius of d's. All right, now we'll see what are the applications of this? Applications of cyclotron. Okay, so I'll just write the parameters here, what we have learned. I'll write down the parameters. Time period of revolution, of revolution. Okay, so what is the expression for that? 2 pi m by qv. Okay, then what is maximum kinetic energy, or we can find out what is frequency as well. Frequency of revolution, 1 over t, that is qb by 2 pi m. Okay, and maximum kinetic energy, ek max, q square b square r0 square divided by 2m. Okay, so these are the parameters we have learned. Now we'll see application of cyclotron. Application of cyclotron. So what are those applications? There are important application is actually to accelerate the charge particle. Okay. Number one, to accelerate charge particles. Charge particles to a very high energy. And this, this energized ions or charge particle is actually used to bombard a nucleus. Okay, bombard the nuclei and study resulting nuclear reactions, and hence investigate the nuclear structure. Generally, this high energy particles are used just like Large Hadron Collider. You might have heard of this. So this is that also works in the principle of cyclotron, and in fact that is the cyclotron itself. But there are many more modifications in that. And when the charge particle gains a very high energy, they are actually they are used to bombard the nuclei such that it can penetrate into the nuclei and get some information about internal structure of nucleus, etc. Okay, second point is that these are actually used in nuclear reactor as well as in atomic. This high energy particles, they are actually used in atomic reactors also. If suppose these high energy particles are actually implanted in solids, it modifies their properties. Okay, so in synthesis of new material, okay, for synthesis of new material, for synthesis of new material, it is used to produce radioactive isotopes also. Let's see here new materials. Radioactive, this is another one used to produce radioactive. So these high energy charged particles which are obtained from the cyclotron, they're used to produce radioactive isotopes. In general, radioactive isotopes are used in cancer treatment. Okay, so there we can use that. It is used to produce radioactive isotopes which are used in hospitals to diagnosis and treatments, etc. So these are few applications or uses of the cyclotron. In fact, cyclotron is used to produce or accelerate charged particles, but it has certain limitations. So what are the limitations of cyclotron? We'll mention first. So limitations of cyclotron. See, it cannot accelerate, cannot accelerate, cannot accelerate, cannot accelerate neutral particle, cannot accelerate neutral particle. Okay, neutral particles. And since mass of electron is very small, so very small, mass of this electron is very small, then what happens while accelerating the electrons, its speed becomes such that its mass neither, like mass is no longer at that very high speed. See, speed becomes nearly equal to c. So at that particular velocity or at such high velocity, the mass will be relativistic mass, not the rest mass. Rest mass is this, and this is, I'm sorry, this is rest mass. This is rest mass. Rest mass. Okay, so this mass becomes variable. When mass becomes variable, see, frequency depends on mass. If you remember, frequency depends on mass. So if the mass increases, mass actually increases. Okay, for electron, mass increases while accelerated. Okay, see, because see, v and c, they are actually nearly. So when speed of anything in this universe is comparable to the speed of light in vacuum, then that body is called relativistic velocity, uh, and mass of that particular object will be increased. Okay, but this increase is not very large. This is, but still, if this increase in mass of electron uh, drive the electron into so as the mass of the electron increases, this will be actually thrown, the electron will be thrown into non-accelerated state because the electric field is there, right? So frequency of this oscillation will change if the mass changes, as well as the frequency of alternating voltage will not be able to synchronize, or there will be no resonance. Okay, the frequency of revolution of electron will change anyway, that will be variable. At the same time, the electric field, electric alternating electric field what we have used, the frequency of that electric field will not match with the frequency of this electron, and hence electron cannot be accelerated through cyclotron. Now, yeah, so I have already discussed this. So the limitations, neutral particles cannot be accelerated. Okay, so cyclotron cannot accelerate neutral particles. Second thing is mass of electron. See, electron cannot be accelerated through cyclotron, and for that, there will be a synchrocyclotron where the alternating frequency is so adjusted that uh, the variation of the mass, due to variation of mass, its frequency and the frequency of the electron can be synchronized. Okay, now we have discussed what is synchrotron, sorry, a cyclotron. We'll try to get some numerical problem out of this topic now. Okay, cyclotron, we'll try to get some numerical problems. So there is a question in JEE Main. we'll just discuss one numerical problem. So the question is proton, deuteron, and alpha particle of same kinetic energy. So suppose a proton, alpha particle, and deuteron, I am writing small d. They have same kinetic energy. Okay, Ek, same Ek kinetic energy. They are moving in a circular trajectory in a constant magnetic field. They are all moving in a same constant magnetic field in a circular trajectory. Radii are given as R proton, R alpha, and R deuteron. So you have to find out which one of the following option is correct. R alpha, R deuteron, R P. This is the radii of circular path, okay, of the charged particle. Whether they are equal for all of them, or option 2 is saying whether this is greater than RD, A means alpha, or this, or so option C is saying whether it can be R alpha equal to R proton, that is less than deuterium. And last option D says whether it is R alpha equal to RD, and that is less than RP. So what are the informations given here? Proton, deuteron, and alpha particle of same kinetic energy are moving in a circular trajectory, like moving in circular trajectories in constant magnetic field. Radii of proton, deuteron, and alpha particles are respectively Rp, Rd, and R alpha. So which one of the following relation is correct? See, what we know about radii. First of all, we need to know that so radii for a circular path, they have say m square by r, that is equal to qvb, right? So from here, let us see how we can write kinetic energy. Half m v square, half m v square. Here actually v is this. So this is v. V is qb by qbr by m. Now, if I find out what is half m v square, so that is the kinetic energy. So this is kinetic energy Ek. See, half m v square means, or v square means, see, this is equal to 2k 2ek m. I'll go to the next page. So we get v square is equal to 2 mek. Okay, 2 mek, and Ek is the kinetic energy. So we actually have v is equal to qb r by m. Then v is equal to square root of 2 mek, or This is B is equal to Q B R by M, right? So we have to find out R from here. This is equal to this part. Into M by QB. Or we can do one thing. So in the expression of radius, what is the role of kinetic energy? Okay, so I'm sorry, there is some problem in this. Let us see. Okay, let us see one more. Kinetic energy is half mv square, right? Half mv square. So let us write this 2k 2ek by m, and let this be q square b square r square by m square. Okay, so this one m will go away. So 2 mek by qb, this will be like this. So there is a relation between kinetic energy and mass, charge, okay, but for different particle like alpha particle, proton and deuteron. So in all cases actually masses are different and their charges are different. Okay, so we can see here, I can write this is directly proportional to m by q. So this I can write, isn't it? Q square b square, here it is actually root over of 2 mek by qb. So we can see that R really is directly proportional to m root over m and this. Okay, I think things were all right. So anyway, so look, this is R is then 2 mek by q into b. This is what we were getting. Then we can actually find out, say, rp by rd. rp by rd, this I can write, see, mp by qp or qd by md. Okay, So this is how, if we compare, I think somehow there is this term will be, let me cross check once again. mv square by r is equal to qvb. This would give one b out of this, q r b by m. Okay, so now half mv square is equal to ek. Okay, so v square is equal to 2 ek by m, right? So from here, v is equal to square root of 2 ek by m. Okay, this is super fine. So r will be m by qb into v. We have got this 2 ek by m, right? So this will be ultimately, if I go with this, 2 m ek by q square b square. Okay, if it goes inside the rule. Now let us check. So what we get from here, r is equal to 1 over q into b, and this is root over m into ek. This is what? So r is directly proportional to root over m and inversely proportional to q. So rp by r alpha is m alpha by root over m alpha by q alpha. Sorry, p by this p into q alpha by m alpha down. Okay, so this will be the case here. So q alpha is, the like deuteron you have 2, so q alpha also 2. Alpha particle 2 Hc4, right? Hc4. So 2 into 1 proton or electron. Alpha particle. Deuteron actually has 2 electrons. Deuteron has more mass. Okay, that is what it is. So qp by q alpha, qp by q alpha root over mp by m alpha proton. So qp by q alpha, alpha is 2, this is 1, this is 2, m proton and alpha 4 times actually. So mp by 4 mp. Okay, so this will be q alpha is 2q actually, 2q, proton is 1, so that is what. So this will be actually 1. Okay, this will be 1. What about r d and r p? We're keeping rp both front, so rp by rd. So rp by rd, this will be qp by qd mp by m deuteron. So proton is mass 1, deuteron is also 1. That factor is 1. Mass here, proton is actually half of deuteron. So this will be 1 over root 2. So we get Rp by R alpha into Rp by Rd. So if we simplify it, R alpha, Rd and Rp, sorry, Rp, R alpha, Rd. This ratio is actually obtained as 1 is to root 2 is to 1. So the option R alpha is equal to R deuteron sorry, this option will be correct. RD. Okay, so this is conclusion. All right, so we'll take up numerical problem in the next class. We'll solve regular problems from JEE papers and NEET papers on this particular like magnetic charges by Savart law, and also from synchrotron, cyclotron, etc. Okay, so thank you for your presence. Bye for today.